Okay, so off we go. Last time we were talking about differentiability, and brings up a pretty reasonable question. If you want to know if the function f is differentiable, how do you know? And this is little consolation to that question, because this is super hard to deal with. One thing you might notice, approaches 0 as x approaches a, right? So this business about x approaching a, that means we're looking at a multivariable limit. And you might have noticed we kind of skipped that section, right? So there's a bunch of formalities that have to go into defining exactly what that means. And the good news is it means exactly what you think it means. The bad news is how you check for that is actually a much harder problem in multivariable calculus than it is in single variable calculus. And so there's a lot of sticky wickets in dealing with this definition of differentiability. Well, we're going to have a bunch of theorems that we're going to be working with that say if a function's differentiable, then good things happen. Right? So we need to know when a function's differentiable, but the definition of differentiability is annoying. And so that's why we care about this related but very different idea called continuous differentiability. Related but very importantly different. So a function's continuously differentiable if a couple of super easy to check conditions are satisfied. You just need to look at the partial derivatives, make sure they exist, make sure they're continuous. It's really easy. Partial derivatives, for one thing. World's easiest derivatives to compute, right? That's nice. Checking if they exist. I mean, you look at it, right? You make sure there's no explosions. You make sure you're not taking a log of a negative number or dividing by 0 or something like that, right? So that's usually pretty straightforward. And continuity, now again, I've kind of swept a lot of that under the rug, but as y'all may recall from single variable, a function is, most functions are continuous where they're defined. Most functions that we will deal with in this course and that you will deal with in engineering settings are continuous where they're defined. So that tends to be an easy thing to kind of just observe. Okay, so now who cares, right? We have a completely new definition of a different term. Continuously differentiable does not mean the same thing as differentiable. It remains that we need to know when is f differentiable. And so that's why we love this theorem. This theorem says that if you have a continuously differentiable function, again, easy to check. Gotta love it. Super easy. Eyeball glance in most cases to check that it's continuously differentiable. Then you get to immediately conclude that the function's differentiable. It's really, really nice theorem. So, for example, let's look at this function right here. Excuse me, and let's decide if this function's differentiable. Now, you could, I suppose, take this function and play this game. And again, there's a lot of it gets annoying. It's very difficult, inconvenient at best, to deal with this definition. So we're not going to do that, like really hardly ever in this class, if at all. What we're going to do is just argue, okay, well, look, it's perfectly easy. This is a polynomial, so its partials are all going to be polynomials. That's perfectly obvious, right? We know from single variable calculus that polynomials are all continuous. That's, again, kind of old news. So we have a function here where the partials are all continuous. That is the definition of continuous differentiability. So again, pretty easy observation. This function's continuously differentiable, and then this theorem kicks in and allows us to conclude that therefore it's differentiable. So it's a kind of a, I guess you might say, a 4-step process here, but there's easy little short little steps, right? And so we get what we want without having to deal with the ugly. How we doing? Everybody on board? I'm going to make a quick comment on an exam, hypothetically, if there were a question that says, hey, is this function differentiable? Well, first of all, this is how you're going to do it right here, pretty much. Right? Obviously, the details will be different. And you can look back to my old exams. You'll notice there are some such questions. It's been done before. It'll be done again. Make sure you explain your reasoning. Right? It's very easy to skip over, and again, it's easy to kind of confuse yourself into thinking that this is the most important part of what's being written down. It's just that you come to the right conclusion, and that how you get there, whatever, it doesn't matter. No, nonsense. Again, I've said it before, say it again. The reasoning is what's important in this course, right? So make sure to show all the steps. Right, it's easy to kind of gloss over some things. So, for example, if a student were to maybe forget to say this part here. If a student were to say, okay, well, the partials are polynomials, right? True, good. Polynomials are continuous, right? Absolutely. And therefore, this function's differentiable. Oh, hey, what happened there? Do we have a theorem that says that if the partials are polynomials, then it's differentiable? I mean, we just don't quite have a theorem that says that, right? There is a key idea that allows this conclusion to be drawn, and that is that the continuity of the partials allows me to conclude continuous differentiability. That's the missing link, right? And that has to get said. You have to say it because it's part of the material for the course, and it's not to be we can't assume that you know the material of the course. The purpose of a test is for you to demonstrate that you know the material of the course, right? So anyway, make sure that you think through what are the ideas that are actually being used, and that you document that, however tersely. Like look how short this is, super short. Right? You don't have to write an essay. Right? But make sure that the necessary parts of the reasoning are demonstrated in what you've written. Does that make sense to everybody? Okay. All right. Okay, here's a related fact. And again, I'm not going to get into the analysis of why this is true. There's a version of this in single variable. I think this is pretty believable. If you have a differentiable function, then it has to be continuous, as it turns out. Again, it's not hard to prove. It's just a digression. It's not really what this course is about. But I think it's very believable. Okay. Now, so what? It's rare that we're going to be using differentiability to prove continuity. It's just not what we need, right? So the way we're going to use this fact is by talking about its contrapositive. This is a lovely little construction. If y'all have ever had a course or a part of a course that talks about logic, right? The contrapositive is one of the fundamental sort of constructions of logic. And basically it says if you have an implication, right, if P implies Q, then if the conclusion fails, then the hypothesis must have failed also. And that's all it says, right? So, so if in this case you take the contrapositive, if a function is not continuous, then the contrapositive says the function couldn't possibly have been differentiable, right? And so what we have now is we have another theorem, the punchline of which resolves the question of differentiability. And that is something that we are in the market for, right? So the original theorem, not so much. This contrapositive, quite a bit. So you may recall, we looked at this function right here several pages back. This is my first example of a function where something ain't right. Right? That we had to admit that the linear approximation formula that we had written down as applied to this function was a crash and burn catastrophic failure. Right? Okay. So, how do I prove that this function is not differentiable? as we feel pretty confidently it shouldn't be, right? This definitely should not be considered a differentiable function. Okay, fine, how do we prove that? Well, pretty immediate that this function is not continuous. It has an obvious jump discontinuity as you approach the origin, right? So the function's not continuous, and therefore it is not differentiable per that theorem. Everybody happy? Alrighty. Okay, so moving along. So we're going to talk about something called the derivative now. Now, you'll recall when we first started talking about derivatives, I mentioned there's a bunch of different kinds of derivatives, and this book and most others like to start with partial derivatives. It's an easy foot in the door, it's familiar, it's easy to work with, and that's kind of nice and all. But I gave you all this warning. Don't hang your hat on that as the fundamental notion of how to think about derivatives in this course. Right? Do not set that as the cornerstone of the building of your understanding of multivariable differentiation. It's a tool, but it's really not the best way to think about it. I am now going to show you what I think is the best way to think about multivariable derivatives. So I'm going to start with our linear approximation formula, right? Where, by the way, notice we're going to assume that we have a differentiable function. So therefore this formula makes sense and does what it's supposed to do. Right? All right. Recall that one of the big features of a linear approximation is that it agrees with the original function in value at the point A. So f of A is L of A. And then next, notice I can take this term and kind of subtract it over to the other side. Nothing happened there. That's hardly nothing. Right. And now let's look and see what's going on. What is this saying? What can we interpret from this equation that we are saying about this matrix called df? And let's see what it does. Well, df acts on x minus a. That is, okay, how far we moved in the domain when we were doing the linear approximation. We start at the point A. We move to a nearby, hopefully nearby, point x. And x minus a is how much I've changed the input. That's what we call a input differential. So, by the way, this notation is very standard, dx vector, just saying how far the input position has changed. Okay, input differential. And now let's think about what we've got coming out on the right-hand side. On the right-hand side, we have L of x minus L of a. Remember, L is our estimate of the value of the function. So L of x minus L of a, if you think about it, is our estimate of how much f has changed. It's not the same as how much f has changed, but it's our estimate of how much f has changed. And estimates of output changes, also called differentials. These are our output differentials. So, what does df do? df is the thing that turns input changes into output changes. And you're going to recall what I put in the box at the very start of our discussion of derivatives was that's what makes something a derivative, most fundamentally. All the different kinds of derivatives we're going to talk about in this class, yeah, they're different and they do different things in different contexts and different ways, blah, blah, blah. But they all relate input changes to output changes. And what we're seeing here is that is exactly what df does. So I nominate, I think this is very reasonable, and by the way, this is very standard, that this is what we should call the derivative. Because in the most general sense, multivariable inputs, multivariable outputs, viewing the inputs as being able to change in any direction, none of this only moving in the direction of one variable. Let's play make-believe and hold all the other variables constant. No, that's come on, that's not realistic in the vast majority of cases, right? You look at the outside world, is there only one thing changing at a time? No, of course not, right? Things are constantly, everything's changing all at the same time. So in this most general sense, the derivative matrix is what turns input changes into output changes. So this is what we call the derivative, and being as it is a matrix, it's sometimes called the derivative matrix. And being as matrices are linear transformations, this is sometimes called the derivative transformation. This is where I would like y'all to hang your hat. This should be the cornerstone of the building of your intuition about multivariable derivatives. Derivatives are matrices. Yes?
If for whatever reason on a test you get a single variable derivative,
yeah.
Is it fine if we just call that the derivative? Like,
no, yeah. No, I mean, if the function truly is a single variable function, right, then yeah. And if you think about it, one variable in, one variable out. One input variable means the derivative matrix would have one column. One output variable means it would have one row. It literally would be a one-by-one matrix, that one element of which would be the single variable derivative. So yeah, they're morally the same when in any possible overlap of possible source of confusion. Yep. Is that cool? Yeah. Right. Okay, so again, cornerstone point of view on differentiation, derivative matrix is the derivative. Okay. All right. So here's, by the way, just kind of a picture. Let's see here. Let me, here we go. I just like to get this geometrically on the screen. So we had this idea that there's a dx input change, and the matrix is what turns that into output differential. And so let's just draw the picture of that. Well, dx representing your displacement in the domain. By the way, you'll notice the picture I've drawn here is my literal picture of a function, right? So we've got the domain on the left, target on the right. The function is taking points on the left to points on the right. There's our dx vector. Here's the resulting df vector. And the derivative matrix is the thing that turns that input vector into this output vector. Is that cool? Yeah.
I was just wondering, why does it also sometimes written as JF?
Yeah, that's right. J is for Jacobian, named after a mathematician named Jacobi. So yeah, it's just an alternative. The very first multivariable class that I took, the instructor, he was a JF kind of guy, right? And so I grew up kind of calling this matrix JF. Yeah, and there are situations where you want to distinguish between the matrix and the transformation that it represents. In which case, yeah, it's kind of convenient to use J to represent the matrix and D to represent the resulting transformation. We're not going to worry about that, and for whatever reason, this is a DF kind of book, so that's why I'm doing it. Yeah.
So in this case, F is going from R2 to R2.
Yep, that's right, exactly. Two input variables, X and Y, two output variables that I haven't labeled because we don't need them for any particular reason. Yeah, totally. Now, while we're here, I want to point out, I want to emphasize, it looks like DF is taking inputs to outputs, doesn't it? Yeah, right? Look at that. It's an arrow. It's taking stuff on the left and stuff on the right. But very importantly, it's not taking points. It's taking differentials, right? So input points and output points, right? The thing that takes A to f of A, that's the function f, right? F takes points in the domain to points in the target. DF takes differentials in the domain to differentials in the target. Does everybody see that difference? Okay. All right, now here's a little twist on it, and I'm going to sweep a bunch of formalities under the rug just to make this as intuitive and convenient as possible. I'm going to take that equation, I'm going to divide by dt. Right? And so we had previously, been looking at this equation. That's now turned into this. And let's think about what this says. This says that the derivative matrix is the thing that turns, okay, well that's, let's see, what is this thing right here? dx dt. It's not a differential. That's a derivative. Right? That represents a velocity. We're going to talk more about that in just a couple minutes here. But hopefully y'all have seen this noted in single variable calculus classes, that derivative of position is velocity. Again, more to come later. So this is what I'm going to call the input velocity, not representing a discrete change in position, but representing a rate of change of position. Still a change, but it's a rate instead of a jump. Okay. And then on the right, again, rate of change, derivative, also a velocity. That represents then the velocity of movement in the target. And so alternative interpretation of the DF matrix is, rather than thinking of it as turning input differentials into output differentials, you can think of it as turning input velocities into output velocities. And totally honest, this is kind of my preferred way to think about it. I find it more intuitively satisfying for basically one reason, and that is that here, that DF is an estimate of how much F has changed. It's not exact, right? This is an approximation. I mean, the real change in the function is, let's see here, it's not actually going to be there. It's going to be, nearby, maybe about there or something. So there's an approximating sort of aspect to when you're thinking about differentials. But with velocities, this is all instantaneous, and it's all exact. And so you don't have to say approximately and, round off errors and stuff like that. This is just exactly what it is. So there's something satisfying about that. Okay, now, quick observation. Remember we had this different formula when you had real valued functions and you wanted to do linear approximations of real valued functions, and it involved the gradient. You may recall that was the very, even before we wrote down the DF matrix, that we didn't at that time call the derivative matrix, right? But that's what it was. Before we wrote down the matrix, we wrote down a formula involving gradients, dot product with the gradients. And so you go through that same process and you get this formula here, which again you'll notice is a way of saying, hey, it's turning input differentials into output differentials. And so, all right, well, this is a little unsettling. Do I have to know a different formula for the real valued case compared to the vector valued case? With the vector valued case, it's, the derivative matrix is the thing. Here, for real value, do I have to switch gears and always think about it as dot product with the gradient? And the answer is no, you don't have to. You may, if you'd like, and sometimes this is very convenient. But you don't have to, because the formulas are really the same. And if I can, here we go. So if you look at this expression right here, notice it's vector dot vector. And I appeal to your memories of linear algebra. Vector dot vector is the same as, well, if you take the first vector and transpose it and make it a row matrix instead of a column vector, right? It's vector dot vector is the same as matrix times vector. It's the exact same arithmetic. You're multiplying the exact same elements, the exact same partial derivatives, right, times the dx input differential. So it's the exact same algebra, exact same arithmetic. Think of this, therefore, as just kind of an alternative notation, I guess. You might say, again, this only works in the real valued case, just real valued. Right, but in that real valued case, you've got an alternative notation, and you might say an alternative, point of view on how differentials relate to it. You can think of it in terms of dotting with the gradient instead of thinking it in terms of matrices. So nothing actually different. Yeah.
Isn't the matrix dot, or doesn't the vector dot a vector return a scalar?
Yes.
The matrix dot a vector, or matrix times a vector returns a vector.
If it were just any matrix, then yes, but you got to keep in mind in this real valued case, right? Because it's a real valued function, there's only one output, which means there's only one row. And when you have a matrix with a single row, matrix times vector is scalar. Yeah, good. Okay. Good. Alrighty, so derivative matrix. That's a big hit. That's one of our big concepts for the course. Derivative matrices are the derivative. They are what turn input changes and output changes, and everything else in some sense is kind of a special case of that more general idea. Okay, all right, so off to 2.4. This is a super quickie. Mostly I'm going to leave this for y'all to read. Again, tough choices and all that. Please do make sure to actually read through and make sure you understand all those details. There are a couple of points that I want to mention, mostly just the one point that I want to mention, and I'll wave my hands at something else. But this is a subtlety, and so it deserves mention. So the first thing I'm going to say is that derivatives are linear, and you should think to yourself, when you hear me say derivatives are linear, you should say, well, yeah, of course they are. That was the kind of the whole point of derivatives are represented by the derivative matrix. Oh, I wanted to be in highlighter mode. Derivative matrix. And the derivative matrix is a linear transformation from Rn to Rm, and matrices are linear. That's ancient history, old news. Okay, true. The derivative is linear. Here is a very close-sounding statement that is extremely not obvious and certainly not the same, and that is differentiation is linear. This is a very different statement. The act of differentiation, right, the act of turning an appropriately nice function into a derivative matrix, that act is not to be conflated with the matrix itself. There's the thing that you get, namely this matrix that we call the derivative matrix, and then there is the process by which I create it from a differentiable function. So we want to make sure to keep those things separate in our mind. Don't conflate df with d, in other words. So here's the very non-obvious statement, and that is that d, the act of differentiation, is linear. I'm going to give you an example in just a second. So let's, first of all, let me wave my hands at a particular aspect of, sort of detail of this, keeping in mind that df goes from Rn to Rm. The domain of df is Rn. Vectors in Rn. And so when we say df is linear, what I mean is if you take a linear combination in Rn, then something nice happens. It's a statement about linear combinations in Rn. Whereas, if you look at the statement D is linear, D's domain is not Rn. D's domain is the vector space of multivariable vector valued differentiable functions. That's not Rn. That's a very different vector space. And the statement that D is linear, therefore, is a statement about linear combinations happening in this very different vector space. So let's see that in action. Literally, we're going to talk about what happens when I take a linear combination of these kinds of functions, and I claim that linearity works. In other words, when you take a linear combination of these kinds of functions, the resulting matrices will be the same linear combination of the otherwise matrices. Okay, so example, case in point. And this is just straight up plug and chug, but here's a couple of functions. There's a function f and its derivative matrix. Make sure you're clear on where that came from and that you can produce that yourself reliably, proficiently, right? Likewise, here's another function, g, and its derivative matrix. Again, make sure that you can do that. Make sure you're reliable and proficient and crisp on what that is and how to do it, and that you can do it yourself. And then here's the combination. Now, for whatever reason, it doesn't matter. I've decided I'm going to take 5 times the first one plus 6 times the second one. This is just an arbitrary example. I was keeping the numbers, convenient but distinguishable. And you multiply that out, and then here's its derivative matrix. Now, nothing happened of interest here particularly yet. I've written down a couple of functions and their derivative matrices. I've taken a combination of them and written down its derivative matrix. And the key, the statement of linearity here shows up by noticing that if you look at that derivative of the combination, and then you compare that to the corresponding combination of the derivatives, right? So here, on the right, I took the linear combination before I differentiated. On the left, I'm taking the linear combination after I differentiated. And the observation of linearity is that these are the same, and easy to multiply that out, right? Take those matrices on the left, multiply and add as indicated, boom, you get this matrix on the right. Yep.
Could you go over the domain of the D function?
Yeah, well, that's right. So D is an action that applies to certain things, and now you just got to think. Let's be honest about it. What are the things that D applies to? Well, D is differentiation. That's something we do to functions. So I'm indicating here that these are multivariable functions. I'm keeping things general, multivariable and vector valued, right? But of course, you can't differentiate something if it's not differentiable, right? So, I guess you could write down the matrix, but it's just a bunch of garbage, nonsense, meaningless, irrelevant stuff. Unless the function's differentiable, it doesn't mean anything. So that's all that is. Yeah, and I claim that's a vector space, and y'all remember all that kind of stuff from 218. Okay. So that's the main thing I wanted to point out, is that differentiation is linear. Again, it's a subtle statement. It's not what it sounds like, but it is true, and it is important to understand. Okay. All right, and now I'm just going to wave my hands. There are various kinds of product rule and quotient rule in various different circumstances. These are in the book. They're equations. You can take a look. They're not hard to confirm. It's just a matter of multiplying it out coordinate-wise. There's no deep water there, but it is stuff that's good to eyeball, and make sure that you're clear on what is it that works out, and that therefore that you can use, and that therefore you should be aware of. So anyway, when you're reading this section, keep a lookout for that stuff. Okay. All right. And now I want to talk about higher order partials. And again, there's not that much going on here. This is what I consider to be kind of the point right here. What is it that allows us to take a derivative of some function of several variables? Well, it's the fact that it's a function of several variables, and then I can entertain, hey, what do I get when I take the partial derivative of it? Okay, well, here's the thing. When you take a partial of a function of several variables, and just think about the mechanics, right? You've got an expression that involves several variables. When you take a partial derivative, you get a different function of those same several variables. And so the fact that you could take the partial derivative of f is the same reason why we can take a partial, or we can at least try to take a partial derivative of the partial derivative of f. Right? It's just like in single variable calculus. A higher order derivative is a derivative of a derivative. No big deal. So here's old news. We've already talked about all of this. If you have a function f, you can take its x partial, you can take its y partial. You get certain expressions. We have certain notations. Right? Make sure you're comfortable with all that. I hope that's eyeball glance familiar. And now, as noted, let's look at the x partial, for example. Notice that is, as promised, also a function of x and y, just like f was. And so I can say, all right, well, what do I get when I take its x partial? Or what do I get when I take its y partial? When I kind of had to bend the diagram a little bit just because I didn't have enough space on the page. So that's that diagram is kind of bending to the left just to keep it out of the way. That's all that is. Okay. So no big deal. I do want to point out the notation. This is confusing notation, but it's ultimately very natural. And what else would it be is a conclusion I hope you'll come to just like I have. Keeping in mind, let's look at the x partial. And let's talk about how we should represent, what notation should we use to represent the y partial of that x partial. All right, well, here you go. Here's one way to represent the x partial that we started with there. Standard notations. How do we represent the act of taking a y partial? Well, with the Leibniz-like notation, we put it on the left like that. That's the notation. Like it or not, that's the standard. It goes on the left. The Newton-like notation, the subscript is on the right. And so, well, I mean, we're in this basically unavoidable situation of, if you then look at how we would kind of compactify these notations, awkwardly, the partial, the indication of the x partial is on the right with the Leibniz notation. It's on the left with the Newton notation, and the subsequent y partial is notated on the left with the Leibniz notation and the right with the Newton-like notation. And so very often students look at this and say, dude, what the heck, man? That seems really wrong. But you look at how this develops, and I think you see this is a corner that we were just painted into. I don't think there's any reasonable... You'd pay a nasty price if you made a different convention to this, such as, wouldn't it be weird if these didn't line up? I think that would be worse. So anyway, heads up, just keep it in mind. You got to worry about which order you're taking the partials. Now, that does bring up an observation, and that is, you'll notice in this case, the y partial of the x partial and the x partial of the y partial happen to be the same. Weird. Right? Lucky? Maybe? Right? But it turns out it's not a matter of luck. And by the way, this is not just for polynomials. This is for a very broad category of functions. This same seeming coincidence will hold for a very broad category of functions. Here's, unfortunately, it takes a little bit of doing to describe what that collection of functions is. We need the functions to be CK. This is the term. You've probably seen an example of this notation back in Calc 1 and Calc 2 long ago. It's probably in the statement of some theorems that you saw, and they may have written it a different way, of course. The K in this notation refers to how many partial derivatives, or in single variable calculus, just derivatives, but here, how many partial derivatives do you have to be able to compute? And the C is the recognition that I don't just need them to exist, I also need them to be continuous. Okay, so again, back in Calc 1 classes, you might have seen that certain theorems only hold if the function is C1. And that's just, again, a little shorthand. C1 just means, the 1 means differentiable, and the C means that, and furthermore, that derivative has to be continuous. aka continuously differentiable. Okay. All right, so with that definition made, then that's the condition. If you have a function that is ck. In other words, if the partial derivatives exist and are continuous up to at least the point k, then, and now forgive my notation here, it takes a little clunky notation to state this theorem. The idea is that these are what we call rearrangements of each other. In other words, if you take a list of indices and shuffle them around in whatever order, those are called rearrangements. And the idea is that if that's what indicates how you've chosen to change the order of the differentiation. Here on the right, I did the j sub k partial derivative first, whereas on the left, I did the I sub k derivative first. So anyway, this is just a fancy notation for representing I'm doing the partial derivatives in a different order. And as the theorem, as I kind of sold this theorem in the first place, what this is saying is you get the same thing no matter what order you do it. Is that cool? Pretty believable, I hope. So the way you're going to use this theorem is, for example, here let me apply this theorem to polynomials. Well, polynomials. Casual observation, partial derivatives are all polynomials. All of them. Okay, and eventually 0, which is a polynomial, right? So all of the partials exist. They're all continuous because they're all polynomials. And therefore polynomials are always CK, no matter what K you pick. No matter how many derivatives you want to take, partial derivatives satisfy this condition, and so therefore, for polynomials, you can take the partials in whatever order you want. Okay, everybody happy? Okay. What do these look like geometrically? You'll notice I'm restricting our attention to graphs. This is where we can make the most useful commentary on this. Things get weird when you're thinking about level sets and stuff like that, so we're just not going to talk about that. But on graphs, in the graph context, what does it look like if you take a second partial? And so, let's think it through. Let's think about taking fxx. What would that look like, fxx? Well, the first thing we're going to do is we're going to hold y constant, as is the rule. When you're taking x partials, y is constant. And by the way, I'm taking the x partial of the x partial, which means y is going to be constant for the whole calculation there. And y being constant means I'm looking only at this vertical cross section where y is constant. Right? Which means that while the entire graph was this giant Pringle-looking shape, I only care about what the cross-section looks like so. So, okay, with that in mind, we're taking a second derivative with respect to x being the only variable. We're taking a single variable second derivative. And single variable second derivatives refer to concavity. This is clearly concave down. Concave down is represented by that being negative. That's exactly what you would hope, right? Exactly the sort of the geometric interpretation that you'd have fingers crossed hoping would work out, and happy answer there. And likewise, and I think this is a good exercise, think through for yourself. I'd like y'all to look at this picture, think it through, persuade yourself. If you have any trouble, come talk to me, of course, but that the y second partial, because of that part of the surface, would be positive. So again, think it through, make sure you're good with that. Okay, here's where it gets weird. And by the way, here's where it gets completely unprecedented. There is no single variable version of what I'm about to show you here, like there was here. I mean, this is really kind of ultimately a rehash of an old observation about single variable derivatives. This is not. This is totally different. We're in uncharted territory here. How would we make sense out of this second partial? And I say we're in uncharted territory because as we do this calculation where we're taking an x partial of a y partial, none of the variables is constant throughout the whole calculation. Right? One of them's constant for sort of the first half, but then it's importantly not constant for the second half, and then vice versa. So this is not a single variable calculus problem. And so don't be searching the recesses of your memories of single variable calculus trying to make sense out of, what's this a version of? It's not at all, right? So here's my favorite way to think about it, and I suppose there's different ways to come at this. But let's look first at the y partials. Can we see the y partials on the picture here? And sure we can. Y partials represent slopes of tangent lines in the y direction. So now you'll notice quickly I did not actually draw a surface here. And the reason I didn't draw the surface is that it's hard, right? It just geometric, just artistically, it's hard to represent what I would need the surface to look like in order for this ultimately to make sense. So what I'm drawing here instead is I'm drawing just the tangent lines. So imagine that this is the tangent line to the surface as you go in that direction, again in the y direction. Right? And so you can probably use your imagination. You can imagine that being a tangent line to some surface. And then likewise, that is a tangent line as you move in that same direction, but in a different location, a different point, a little further toward us, and et cetera, et cetera. Right? So these slopes, as we move in the y direction, those are our y partials. Okay. So how do I represent the x partial here? And here's the tricky part. It's tempting to say, well, isn't it slope in the x direction? And it's not. It's importantly not, because very importantly, notice, what are we taking the x partial of, right? You can see it right here. It says we're going to take the x partial, but we're taking the x partial not of f. The picture we're looking at is on the graph of f. That's not what I'm taking an x partial of. I'm taking an x partial of the y partial of f. Are we looking at a graph of the y partial of f? No, not at all. This just isn't a graph of the y partial of f. So I cannot interpret the x partial in terms of tangent lines, because we're not looking at the right picture for that. What I can do is I can say, okay, well look, whoopsie. Here we go. The x partial represents how fast whatever it is that I'm looking at changes as I move in the x direction. Right? So as we have in this picture here, and I just have to do a little bit of hand waving, back in the back, the slope is like this, right? So we've got the surface, the graph of f is kind of sloped this way in the y direction when you're sort of in the back. And now as we move in the x direction, as we come out of the screen, that slope you can see is kind of doing like this, right? Further back it's like this, and then as it comes out of the screen, it's doing more like that. And let's just think about numerically, looking back here, this back slope here appears to be pretty negative. I don't know, about -2. This one here, maybe more like about -1. This one here, maybe -0.5. This one's about 0. This one's getting positive. I think as we're coming out of the page, as we're going in the x direction, I think these y slopes are increasing. Right there. Negative back here, positive out here. So my geometric interpretation here then would be that as drawn here, this expression would be positive. Everybody okay with that? By the way, one thing you're going to notice, kind of intrinsic to how this expression and how it manifests on the graph of f, it kind of represents a twisting of the surface. And that's just kind of intrinsic to just how this plays out. So this is what we call a mixed partial derivative. Mixed partial derivatives represent a twisting of the surface. Okay. Yes?
But if this is the same as df over dx.
Yeah, going the other way, you get the same thing. Yeah, that's right. It is. Now it's a great question, and all I can do is a little hand wave. Okay, but so imagine that I'm grabbing onto the corners of a sheet of rubber here, and then I'd put that twist in it, and it's the same twist I have here. So like this, right? Now notice. Yeah, sure, I'm thinking of it as that I'm twisting it around like an axis like this, but now if you just look at my fingers, right, and I hope I can do this without screwing it up. As I do this twist, looking only where my fingers are, that's the same as doing that twist. My fingers do the same motion there. So in fact, yes, that's kind of intrinsic to how surfaces twist. A twist in one direction really is kind of the same as a twist in the other direction. Absolutely. It's a very surprising kind of geometric conclusion that comes out of this math that we just did. Yeah. And I'm sorry, I see now that we're out of time, so we'll call it there and pick up here on Wednesday. See y'all later. Have a good one. Don't forget to come talk to me if you came in after I did attendance.
Sorry.
Yeah.